Okay, welcome to class 13. Last time, if you remember, we were dealing with the equivalence of NFA, DFA, regular expressions, and we proved that none of them had any more or less power than the other two, than any of the other two. So they all really just are ways of defining regular languages. So if we can make an NFA, we can make a DFA. If we can make a DFA, we can make a regular expression. We have a regular expression, we can make an NFA. So we could do all three of those. They're all equivalent methods of defining languages. Now today, though, what I'm going to look at is something that's can be really useful, and that's minimizing a DFA. So in other words, if I have one of these machines, how do I know if that's the smallest possible machine that I can make that defines that language? And there can be some usefulness as far as optimization. And there can also be some usefulness for proving certain things by having the ability to minimize a DFA and say, this is definitively the smallest machine that I could make, that the smallest DFA machine that I could make that solves this problem. All right, we have quite a few slides here, but they'll go pretty quick once we get into it. So let's go ahead and get started. All right, so here's an example DFA. And you notice it's definitely a DFA. Every state has an A and a B leaving it, so it's a total function. There are no lambda transition. There are no multiply defined edges, but you'll notice that it looks fairly complicated. We've got 6 states. Q0 is our start state, and there's a bunch of states there. But it turns out that this DFA is the same as this one. This one defines the same language as that, so these two are equivalent. And we could actually simplify it even further and say, well, this one is the same as that. So this one up here that had 6 states is actually the same as this one that defines the same language as this one that has 2 states down here. So the question is, how do we get from this to that, though? How would we show that this could actually be replaced by that and be sure without having to just try a bunch of stuff or kind of puzzle it out and try to figure it out? We want to have some sort of algorithm that actually does that. So what we'd like is a way to take any DFA, no matter how complicated it is like this, and then run it through that system and have it produce a DFA that's the smallest machine possible that represents that same language. So how do we do that? Well, to start with is this concept of reduction. So there's 2 kinds of reduction that we're going to use to take a large DFA and then kind of whittle it down or narrow it down to something smaller. And the first kind of reduction that we're going to do involves removing states that we can never get to. In other words, there's no reason to have a state in our machine if we can't get to it from S. And then the second type of reduction is combining states that are indistinct, or combining states that really there's no reason to have 2 states when we can combine them and have 1. So step 1 here, removing kind of those unreachable states, that's generally pretty easy to figure out and easy to do. Combining them, though, is a little more complicated, so we're going to have to come up with an algorithm for that. So let's start with step 1. How do we remove states that can't be reached from the start state? All right, so the way we do that is we just start with S, and we just follow arrows. We don't care what symbol it is. We just follow arrows and mark any state we can get to. So if I start with Q0, I got to Q0, I mark it. That one's good. We have to keep it. And I followed an arrow A and B. I got to Q1, mark it, keep it. Followed an arrow, got to Q2, mark it, and keep it. What are all the arrows I could follow from this? Well, I could stay there. I could go to 3, mark both of those and keep them. And then from 3, I could get to 4, mark it to keep it. And then from 4 back to 2, already marked. And so I have all of them now marked except for Q5, which was unreachable. There was no arrow. There's no path from Q0, no walk that led where I could get to Q5. So since Q5 is unreachable, we could just get rid of it. So we just deleted it, erased it, any edges that came from it or went to it. And it could be there's more than one state. We could have a whole cluster of them over here that were unreachable from S. Just get rid of all of them and all of their edges too. So now we're left with this. So we haven't minimized it yet, but we've gotten rid of some things. So the next part of this is combining states that are indistinct, or states that there's no reason to have 2 of, where they kind of are doing the same thing. And that's what we're going to do next. So the first thing here is I want to cover is, what does indistinct actually mean? So that word indistinct, probably the best way to understand that is to do a few examples. So let's look at a couple examples of this. So the first example here is looking at this example here. Are there any states that are indistinct? And in this case, it turns out that this is the same as that. And in other words, Q1 and Q2 are indistinct from one another. Now, how do we know that? Well, the way we know they're indistinct is that both of them are final states and both transition out of that identically. So Q1 on A went to 3, Q2 on A went to 3. Q1 on B went to 3, Q2 on 3 went to B. So on the same output symbols, leaving that, the same edges, went to the same place in each of those examples. So they both did the same thing from that state. Now notice it doesn't matter how we got to that state, all that matters is what happens after it. So if both of them are final, or both are non-final, and they both have the same resulting output from them, the place where they go to, on the same symbols, then there's no reason to have two states. We could combine these. And that's what we did here. We combined 1 and 2 and made 1. And so on A, we went to that combined 1-2 state, and on B, we went to 1-2, and so we combined them. So we could combine 1 and 2 here, and basically think of it like put a dotted line around both of those and make it this new kind of defined state. Now, there's another example, though, that we need to look at, too, in understanding that. And this one's a little more complicated, so we're going to look at that. So we've got this DFA here, and in this case, that's the same as that. So in this case, we actually had two sets of states that were indistinct. These two here and those two there. And so what we did here is we combined 3 and 4, but you might look at Q1 and say, well, it on B went to 4, where 2 on B went to 3. So these ones can't be indistinct. They can't be combined because they went different places. But there's a little bit of a problem with that logic in that the places they went to, these could be combined for the same reason we had earlier, because 3 on A went to 5 and B went to 5, and 4 on A went to 5 and B went to 5. So 3 and 4, it doesn't matter how we got there, 3 and 4 can be combined, and if 3 and 4 are combined, then 1 and 2 now both go to the combined state 3, 4. They now do the same thing, so these can also be combined. So because of that, 3 and 4 could be combined, and now that has made 1 and 2 indistinct, and they can be combined, which is why we can get this out of that. So given those examples, if we came up with a definition of what makes two states indistinct, we would come up with something like this. So what makes two states indistinct? Well, two states are distinct if and only if they are both final or they're both non-final. So in other words, you can't have one that's final and one non-final. You could never combine a final with a non-final. You're not allowed to do that. But we could combine two finals and two non-finals. But that's not enough. We also have to say for all the symbols of the alphabet, they both transition to the same states or to states that are themselves indistinct. So in other words, we have to have the same action. They have to produce the same result given the same input, or the thing they transition to has to be already marked as indistinct. So we're going to come up with an algorithm to minimize any DFA. So here's the algorithm. Step 1, we make a table of all pairs of states. So it's every state versus every other state. So for example, we have Q0, Q1, we'll have Q0 versus Q2, Q0 versus Q3, Q1 versus 2, 1 versus 3, 2 versus 3, however many we have. It's kind of like think of it like a round robin bracket where every player plays every other player. They don't play themselves. So it's kind of like if you ever looked at a tournament sheet with a round robin bracket where the names of the players are kind of on the rows and the columns, the places where the row and the column meets, that is a pair of those two things. Now we're going to set each of the positions in that table to unmarked. So think about this as like a round robin table of every state versus every other state. And they haven't played a game yet. So they're unmarked initially. Step 2 is we go through the table, and anywhere we have a state versus another one where one is final and the other one's not, we mark that one. So a mark means these are distinct. They could not be combined. So a mark so this is kind of like a distinctness table that we're saying a mark in that table means these two could never be combined. So we're marking anyone where one of them is final and the other one's not, no matter which way that goes, we're marking that as could not be combined. So we're marking that place in the round robin bracket as this match has been played. These could not ever be the same. And then we're going to enter this loop, and we're going to loop until we make a pass through the table where no marks were made. And what we do is for each pair of states in the table and each character of the alphabet, we're going to check to see with those two states, if it's unmarked, we're going to check it. We're going to say, hey, let's see where it went on the letter from the alphabet. And if the place it went to in the table on that letter from the alphabet is marked, then we're going to set this pair as marked also. If the place it went to was unmarked, then we just go on to the next letter of the alphabet or the next pair of states. So in other words, this is going to be like a for loop that runs through every unmarked state, and it's going to check to see where did we go on every letter of the alphabet, and if I went to a place that was marked as could not be combined, then these ones could not be combined, so we have to mark these ones as well. So once we've made a whole pass through the table where no pairs, new marks were added, then any ones that remain unmarked in the table can be combined because those ones are indistinct. Probably make a lot of sense to look at an example here. I think this will make more sense once we do that. So here's the example. And the example that I want to run through here is that one we had from earlier. So we already know what this is going to look like when we're done, but let's go through it anyway. So step one, make a table of all pairs of states, QI versus QJ. We've got 6 states. So here's the table. Notice that I'm writing them the names of the states on the diagonal. So let's look at these cells for just a second. So this cell here is Q0 versus Q1. Could those be combined or not? And this state down here is 0 versus 2. So in other words, you just follow the column down, and then whatever row we hit, that's the one that we're comparing. Q0 versus 1, 0 versus 2, 0 versus 3, 0 versus 4, 0 versus 5. The next column is 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 2 versus 3, 2 versus 4, 2 versus 5, 3 versus 4, 3 versus 5, and then 4 versus 5. So this is all of the, again, this is like the bottom half of a round robin bracket kind of group with all of them going down like that. So this is every state against every other state. So that was step one. Step two, we want to mark all of the pairs where one is final and the other is not. So in other words, if we look at 0 versus 1, 0 and 1, that's still on the table. Well, 1's final and 0 is not. So we need to mark that. Those could never be combined. So we're going to do that for all of them. And we end up with this. And to make it easier to see, I bold-faced the ones that are final states here. So you can see. So anywhere we have a non-bold and a bold, I put a mark. So that gives us this initial table that we have right now. Now we're not done yet. We have to go through step 3 where we iterate through all of the ones that are unmarked and then see where they transitioned on each of the symbols. And if it went to a place that was distinct, that one also has to be distinct. When I write these out on paper rather than bold-facing them, I'll put circles around the ones that are final, and that makes it easier. Say if you have a circle and a non-circle, you put an X in the table there. Again, this X means could not be combined. That means marked. All right, step 3. Step 3, go through all unmarked pairs for every symbol. So let's start with the first one in the table. So 0, let's start on 0 here. So 0 versus 3. So in other words, 0 versus 3 on A. Well, we look up the transition function. So 0 on A went to 1, and 3 on A went to 5. So then we look up in the table at 1 and 5. So 1 versus 5, there's 1 versus 5. That's unmarked, so we go ahead and move on. And then we look at 0, 3 on a B. So 0 on a B goes to 2. 3 on a B goes to 5, so we have 2, 5. We look up in the table, 2, 5, that cell right there. That's not marked. Move on. Now we're done with the pair 0, 3. We're done with that one. We now move on to 0, 4. So we're on the one right below it right there. So 0 on an A, 4 on an A. So 0 on an A goes to 1. 4 on an A goes to 5. So we have 1, 5. 1, 5 is not marked in the table. So we move on without adding anything to the table. Next one is 0, 4 on a B. 0 goes to, on a B goes to 2. 4 on a B goes to 5, so we have 2, 5. We look up 2, 5 in the table. 2, 5 in the table, not marked, so move on. Now we're up to this one right here, 1 and 2. So 1, 2 on an A. So 1 on an A goes to 3. 2 on an A goes to 4. So we now have 3, 4. 3, 4 is unmarked, so we move on. We now have 1, 2 on a B. So 1 on a B goes to 4. 2 on a B goes to 3, so we have 4, 3. So 4, 3, we look that up in the table. 4, 3 is unmarked, so we move on. Now I've just collapsed all of these up on this step, so it's easier to see. So anytime there's one that's unmarked, we just go on to the next one. We don't do anything when we see that. So now we're up to 1, 5. So 1, 5, we're on this cell right here. We're deciding if we need to mark that. So 1, 5. So 1 on an A goes to 3. 5 on an A stays in 5. So we look up 3, 5 in the table. 3, 5 in the table is marked. So because that's marked, we now also have to mark 1 and 5, which was not marked before. So we're adding that one. We've just added this highlighted yellow one in. So that one we have now marked. And then we're going to go on to the next pair. Once we've marked that, there's no reason to check 1, 5 on a B. So as soon as we make a mark, we just go to the next pair. So the next pair now is going to be 2, 5. So 2, 5 on an A, we look up Q2 on an A. Q2 on an A goes to 4. Q5 on an A stays in 5. So we now have 4, 5. We look up in the table 4, 5. 4, 5 is marked. And because 4, 5 is marked, we now have to mark 2 and 5. So we now add that to the table. So 2, 5, we've added this new mark there to the table. And we've marked that. We only have one left now, and that's 3, 4. So 3, 4 on an A. So 3, 4 on an A, they both go to 5. And table 5, 5, there is no cell 5, 5 because 5 is the same as 5. So since that's the same place they went to, we move on. They're not distinct. It is the exact same thing. So whenever you get the same value from this, and it refers to a part of the table like over here where it's 5 versus itself, those are not distinct, so we just move on. And now we look up 3 and 4 on a B. So 3 and 4 on a B, they both go to 5. 5 and 5 are the same, so we move on. And that ends the first pass through our table. So we're done with this pass. And because we made a mark during that pass, we're going to go through again. So we're going to go through the unmarked pairs again. So now we're down to 4 that we added 2 to this. So now we have these 4 that are left that are unmarked. So now let's look at 0 and 3. So 0, 3 on an A. 0 on an A goes to 1. 3 on an A goes to 5. So 1, 5 is marked. So 1 versus 5 is definitely marked. And that means we need to mark 0, 3. So 0, 3. We add the mark to that one. And we go on to the next pair. The next pair is 0, 4. This one right here. So 0, 4. So 0 on an A goes to... and here, I just realized that it's covering up part of the picture up there. Let me turn off my face. All right, so 0 on an A. 0 on an A goes to 1. 4 on an A goes to 5. So now we have, now we have 1, 5. And 1, 5 is marked, so we need to mark 0, 4. So 0, 4 is marked. Go to the next pair. The next pair is 1, 2. So that one is unmarked. So 1, 2 in the table. So 1 on an A, 2 on an A. So 1 on an A goes to 3. 2 on an A goes to 4. So now we have 3, 4. 3, 4 is unmarked. And because 3, 4 is unmarked, we just go on and try B with 1 and 2. So 1 on a B goes to 4. 2 on a B goes to that. So now we have 4, 3. 4, 3 is unmarked. So 4, 3 is that same cell. That's unmarked, so we move on. Q3, Q4 on an A. So now we're on this one. So 3, 4 on an A, they both go to 5. That's the same state, so we move on. And then 3, 4 on, actually this should be a B on this step. Let me fix that real quick. 3, 4 on a B. On B. B. So 3, 4 on a B goes to 5, 5 again. And I got to fix this one too. Okay, so that on a B is the same state. So we're done with pass 2. And I suppose I should fix this one too. And now that we're done with pass 2, we did make a mark during that pass, so we need to go back to the top and go through one more time. So because we made a mark during pass 2, we're going to go through the unmarked states once again. So we have 1 and 2 and 3 and 4. We only have 2 left now. So 1, 2. So 1, 2 on an A gives me 3, 4, which is unmarked. We move on. 1, 2 on a B takes me to 4, 3, which was the same one. It's also unmarked. We move on. 3, 4 on an A takes me to 5, 5. Those are the same state. Move on. 3, 4 on a, apparently made the same cut and paste error multiple times here. And again, that's the same state. So move on. Here, I know how I'm going to fix this. I'm going to all right, so those are the same state. So we're done with pass 3. No new marks were made. And we now have the final table. I'm going to go ahead and just pause for a second here. And I'm going to fix the next slide where that same cut and paste error was. And then I'll resize my face so you can still see me up there in the top. And I'll be right back. Hold on one second. Okay, so this has been fixed. And now you can see me again. And you can see the whole DFA that we were starting with up there. So we've made it through pass 3. No new marks were made, so we didn't add any new marks here. So now we have our final table. So this is our final table. So what does that mean that that's our final table? So now that we have the final table, we've exited step 3. We've finished that for loop. We're now in the final thing that we do. So any pairs in our final table that are unmarked are indistinct from each other. So in other words, 1 versus 2 did not have a mark. So because pair 1, 2 was not marked, we can combine 1 and 2 into a new state, or a single state. And 3 and 4 also doesn't have a mark, so we can combine those two together. We can't combine all of them together. We can only combine 1 and 2 and 3 and 4 into their own states. So that's going to give us this, where 1 and 2 now looks like that. 3 and 4 now look like that. And this is now our DFA, and that's guaranteed to be the minimum size DFA. So our original looked like that. Our minimized one looked like that. We didn't have to think about it. We didn't have to do anything but go through the algorithm. You could actually write a program that does that for you. The cat is purring. Cat's very happy about that. So we could write a program that does that. And essentially, we feed in a DFA. It outputs the smallest one possible. Now, there are some applications for that. And this method will work on any DFA. It doesn't matter how many states it has, how big it is. We could actually minimize it and get it down to the smallest number of possible states. And if you think about the fact that like a microprocessor is really just a big state machine, a big DFA that has a bunch of transistors, you could actually use this method to make something like a microprocessor that uses some other kind of circuit or some other kind of system that uses the smallest number of transistors possible. Or we talked about DFAs being used for like game logic for AI, or for an elevator control system to keep track of the states of the doors being open and closed. So this allows us to have a technique now that I can say, hey, here's a machine that does what I want it to do. Make the smallest machine possible that does that same thing for optimization purposes. All right, so we can take any DFA and always produce the smallest possible DFA can be made for that language. And that can also be useful, as I said very early on, for proving certain things. An example of that would be, let's say we want to prove that two regular expressions represent the same language, or whether we definitively want to show that they represent different languages. Well, this is a case where that DFA minimization technique could come in handy. And here's how. We basically take the two regular expressions, make an NFA for each of the two. We then convert each NFA to a DFA. Now, those DFAs might be different at that point because the NFAs might be different, but we'll have these two different DFAs. How do we show that one DFA is equivalent to the other? Well, we minimize each one, and then that minimized DFA that we come up with will be the smallest machine possible. And if those two machines are identical, the smallest machine that got created was identical, had the same number of states, had the same transitions from each of those states, then we know the regular expressions that we started with had to be equivalent as well. And that's actually a pretty powerful thing to do. So you might take a regular expression like, I can't tell if this represents the same language or not. I can put strings into this one and see if they're in the other one. I could try this and try that. But that's not really a proof because you'd have to try every possible string, and they could be infinite-sized languages, so you couldn't test everyone. But if now the cat is shoving things on the floor. Hey, don't do that. The cat's taking a circuit board I was working on and pushing it onto the floor because cat reasons. But anyway, that's a really powerful thing to be able to take those those regular expressions and definitively prove, yes, these are the same. But not only that, but now we have produced a machine that's the smallest machine possible that will act as a recognizer or act as the definition for that language of those regular expressions. So you might have a really large regular expression, super complicated, tons of clauses in it, and you can boil that down to the smallest machine possible. And then you could take that machine and make a regular expression back from that and have a reduced, minimized DFA for that. Okay. If any of that was confusing, I'd encourage you to go back through that process and look at it again. We will have a quiz doing that, but it's really not too bad. Let me just back up here for a second. Looking at, if you go through the thing and keep track of the parts in the table, the main thing to do is just kind of be systematic about it like we did here and filling in that table. And once you have that final table like this, it's really easy to say, well, Q1 and Q2 are the same, Q3 and Q4. And there are cases where you'll wind up with 3 or more that are the same. And in that case, you'll have a cluster of like 2, 3, and 4. If they combine, you'd have all 3 of these cells here unmarked. So 2 is the same as 3, 2 is the same as 4. Therefore, 3 is the same as 4, and 2 is the same as 4. So all 3 of these could then be combined. So you will have cases like that. Okay, so that's it for today. And work on your conversion lab. I think I will be available next class to help you with that as well. So I'll probably send out an email that says as much. So I'll come in and help answer any questions. We're also going to have the midterm coming up shortly, so be ready for that. I am going to post a study guide and make the announcement probably next class about the midterm, show you the study guide and what to do on that. And then I'm going to give you some time to work through that and ask me questions where I'm going to come in to class. So do practice this because we will have a quiz next class on this DFA minimization. We'll do a couple of those on a quiz, and there'll be some of those on the midterm. So make sure you, even though we haven't had homework doing these, make sure you look at that methodology. All right, so that's it for today. Everybody stay safe, wear a mask if you're out in public, wash your hands, and I'll see you next time.